Is it Christina?
This is how. Hello to everyone. I'm Christina, a software developer of the Institute Langevin is here next to the synchrotron. And I'm here today to present you a project that we have recently developed in our service that we name it RICA, which stands for Remote Instrument Camera Access. And it's a system whose aim is to improve our remote user experience by providing them a real-time video streaming over a synchronized web. So the aim of my presentation is just to describe you how we did this application. So the outline covers the process, right? We start with a little introduction. I will explain the requirements we have for our application. I will talk a little bit about the streaming protocols. You will see why we need to do that. Then I move to the architecture, and at the end of the presentation, we'll talk a tiny bit of authentication and authorization, and I'll finish by the future work of the application. RICA, as I said before, is a tool that provides a real-time visualization of the instrument. It just aims to just address three needs that we have at the ILL. The main one is the most obvious. We needed to see specific areas of the instruments that are often hard to access or even not visible, they're hidden. We needed also, this is more for us, for the technical staff, to standardize all the camera systems that they were already present in our institute. And then finally, we wanted to provide an external access. This goes a lot with the idea of having a remote access to the instrument. This project was developed by the collaboration between two services at our institute, the Service de Contrôle des Instruments and the Service Informatique. What are the requirements we have for the application? What we wanted to provide basically are the following. We were aiming to have a real-time display with no recorder and no user on-demand reposition of the cameras, although we will allow a digital zoom. We wanted to have a control access, so that implies that we will have to only provide access to this video streaming of data to the users that are known by the system. And then we wanted to provide a web application in which we are going to use standard IP cameras like the one shown in the image, and we'll try to aim for an in-house development. Now, why I have to talk about streaming protocols? The streaming protocol is a method, a group of rules that are used to deliver media, which is mainly audio and video over the internet. And at the very beginning of the project, we found out that the cameras that we're going to use, that are IP cameras, cannot be used in a web application because they use a streaming protocol, which is called real-time streaming protocol, that cannot be used in a HTML element. So we had a problem there. We had to just find a solution to see what we could use to display the stream of data in our application. I'm just going backwards, yes. Before talking about the possible solutions we had to our problem, we needed to just see what are the criteria that will allow us to choose for the best solution. So what we're looking for with low latency, as I said, we want a real-time display of the data as much as possible. We will try to limit the disk in writing and reading. We also want to have something that does not really consume a lot of CPU. This on the streaming world basically implies avoid having to transcode the data. By transcoding means decoding, altering, and encoding the data back. And finally, also we want to keep with this open source mind, so we will try to avoid using any commercial software. So what are the options out there in terms of streaming protocols? I just divide them in two categories to make it that easy. On one hand, we have what we call adaptive HTTP-based protocols, which are mainly nowadays two types. They're called HLS and Dash. Those streaming protocols are provide a technology that is called adaptive bitrate streaming, in which basically the client downloads continually the data. And depending on the quality on the network, this data is downloaded in a different bit rate, the name adaptive. They're widely supported, they are extremely scalable, they're everywhere. But they suffer from latency because it's not its main aim. There were some low latency variants being in development when our project was being deployed, but they were not. We couldn't test them because they were in really early stages. Then on the other side, we have what I call the other completely opposite strategy. It's a push-based strategy based on the usage of WebSockets. In this case, we have a server that after a connection to the client just sends the data actively as a stream. They are really simple to set up. They don't have a big latency because basically the client doesn't download any data before displaying it. And this also makes that they don't use almost any disk. As you must have already guessed, we just went for the second option. We were trying to see what we could put on top of the WebSocket for our data, and we found a perfect combination, and it's the following. We just decided to use a WebSocket-based communication using fragmented MP4 on media source extensions. Now, what does it mean? So that means that our server will be divided into applications. We'll have our main server that does the communication between the client and the cameras. And then we'll have to add a new application that we call it a streamer that does the conversion between our initial RTSP protocol to our fragmented MP4. We do that by using the FFmpeg, which is a widely known tool. And it's a procedure that is not as transcoding. We don't change the codification of the stream, we don't change the bit rate, we don't change the quality of the image, we just repackage it. So in terms of CPU, it's quite low consumption. And from the point of view of the client, we will use MSE elements, which are native HTML elements. So it's also, we don't need any special library, nothing really fancy there. So once we had our prototype validated, we decided to move on to a next stage. So we carry on a benchmark to see if we could apply this solution to a bigger scale. I'm not going to give the details about the benchmark. It's not really essential, but just keep the idea of the three following ideas. The streamer load does not depend on the number of clients that are watching the cameras. Basically, we only have a stream converter per camera. We have the server load that depends on the number of clients that are watching. That's normal. It hasn't been the case so far, but we thought about implementing some load balancing strategy if it's needed. And then last of all, and really important, keep in mind the configuration of the camera. Because in fact, a change of the resolution can lead to a quite increase of this consumption of the streamer. So at the end of this benchmark, it was decided that we will add the cameras on the private networks of the PCs that are used to control the instruments. And that leads us to the following architecture. This is a really schematic one, in which we will have a streamer installed in any of the instruments and running, cameras attaching to this streamer via the private network. We will access to the cameras via static IP. And then we have a central server, which does the entry point to the clients. And then just not to forget, we also at the very end of the project, we added a database on the server, which will allow us to get all the, store all the data to configure the cameras and the streamers. So now that we have the application, more or less the architecture is there. As I said before at the beginning of the presentation, we want to provide an external access to our application to see the data from the outside. In the web world, we all know that implies working on authentication and authorization. So authentication is just to know, we need to know who, the system needs to know who the person is before giving access to the application. This we use OpenID Connect protocol for that. And then for the authorization, so now once the user is authenticated, The authorization basically is just depending on some rules, we allow the user to access to different data of the application. In our case, it's quite simple, the rules. We have like two groups. We have the ILL staff, the scientists and technical that have access to the cameras during all the time. We can basically see everything. And then we have the external researchers, the people that come to the ILL to do experiment once in a while. These people will only have access to the cameras in which they are doing the experiment only during the time that the experiment is being taking place. Once their experiment is finished, their streaming, if they are still logging in the application, it's stopped. So this is how it looks nowadays. The screenshot is not really. This is a screenshot of that shows the example of the cameras that are currently installed in an instrument called EN20 at the ILL. The application has been running since the end of 2022 with no major problems. We are giving service to 20 instruments so far. And what are the future work? We are trying to add more cameras. We always are looking for clients. Maybe someone in the audience is interested in the application, who knows? We want to improve in the administration tools that allow us configuring the camera remotely, which is quite useful. Obtaining system metrics that nowadays currently we don't have. I would like also to evaluate the low latency dash, which is nowadays out. So see how it behaves, see how what this low latency represents. And then finally, keeping improving the client, which is just always a task that has to be done. So that's all, thank you. And
Thanks for the cool application and way to stream video. Have you measured the latency?
We did tests on the benchmarking. I didn't put anything because...
Okay, so is it like 10 milliseconds or?
It was a second.
A second,
yeah.
Okay.
Yeah, compared to the dash, we did test on dash. And we were trying to get it really, really low and until it really didn't cope. And dash was like about 10 seconds, like optimized, like until it just didn't start doing nonsense. And this solution is about a second, yeah.
And how does it handle degraded network?
In fact, it doesn't. It's not adaptive. That's why the reason why I would like also to see this low latency. I mean,
so you just drop frames or what?
Yeah, and I mean, it can even end up like disconnecting. I mean, dropping the connection. We have improved the client. It hasn't happened so far because we don't have really. I mean, our data quite often is not really so consuming. We don't have like an image that changes that much. But we have implemented a way that the client tries to reconnect if the connection is dropped, and it works.
Is it already on GitHub?
It's not open source. I'm looking for clients, but it can't be open source, because we develop it, and our aim always is to provide an in-house development. So I don't see why it shouldn't. So yeah, it could be done, yeah, but it's not nowadays. That's why I didn't put any fancy web page on.
I might have missed it, but your digital zoom you allowed, does that happen on the client or does it affect all clients that are looking at the same camera?
It's on the client, yeah.
Okay.
It's just, well, that was the requirements that we had at the beginning that are quite tight. So it's just, we don't want to touch the data because people think that they're being observed, I don't know. And so it's from the digital, if we said, okay, digital zoom, this is the client and you do it from your side. But if the camera provides that functionality, it could be done.
So no AI enhancements of the staff yet then? No AI enhancements of users yet? No,
let's try them to use it, be happy with them and then move on, yeah.
Great. So I'd like to thank you again, wasn't it? All right. Dean.